All right, we'll get going today. Have an announcement first that I was asked to share with you. The American Medical Student Association is having their first general meeting tomorrow. So if any of you are pre-medical students, that's potentially a good organization for you to check out. The other thing I'm doing today, which has immediate drawbacks, is I'm experimenting with a new PDF annotator, although that requires me to seemingly put this video recorder thing in front of it, which is going to be a little bit irritating, so I'll try to get out of the way. Probably the top is maybe better. Okay, so we'll see if this one works, because the one I have been using was lagging quite a bit when I was using it along with the video recorder. The other advantage here is that I have this little laser pointer thing now that I can use, so especially for people watching videos, it'll be a little bit easier. All right, let's get into it then. Now, one thing that I wanted to clarify first that we just ended with last time, there's probably a slightly better way to explain things than I did, and that's regarding ionization energy, which we're going to come back to a little bit at the beginning of today. So remember, what we were interested in was the trend for ionization energy. And so as we go, generally as we go from left to right on the periodic table, so I'm going to draw a little bit of a plot here that has ionization energy on the y-axis, and then I'm going to put the group number on the x-axis. So the group number being which column in the periodic table we're in for the main group elements. So group 1 being the hydrogen column, and then group 2, and then 3, and so on. So we have all these different main group numbers, 1 through 8. And then maybe to orient you, the hard part about this is switching to the periodic table is not as easy. So if we go to the periodic table quickly, just to make sure we're on the same page with what we're doing here, the group numbers are these, we have them as Roman numerals on the top of our periodic table. So the ones that are labeled as A are the main group elements. So group 1A is here with hydrogen, group 2, and then we're jumping over to group 3, 4, 5, 6, 7, and 8. We're not particularly interested in the periodic trends for transition metals in this course, so we'll just mainly focus on the main group. Let's go back to our full screen. All right, so anyway, going with ionization energy then, generally what we have is a linear trend. So as you go from left to right, we said the ionization energy tends to increase, and it's fairly linear for most of the groups, but there are two exceptions we want to be familiar with. So if you have group 2, which has a valence configuration of NS2, so that's going to be a filled S subshell for those group 2 elements, or if you're in group 5, where you have an NS2 NP3, so this sort of half-filled configuration, both of these have abnormally high ionization energies. So remember that ionization energy is the amount of energy that it takes to rip an electron off of an atom, and if they already have a stable configuration, so an S2 configuration is a stable configuration, and then we said that half-filled subshells tend to be pretty stable as well, those are going to have abnormally high ionization energy. It's going to take more energy to remove an electron from there than you would expect. So looking at this trend then, we see that most of these would fall sort of on the line. But then group 2 and group 5 are going to be abnormally high, and they're going to be off of that trend a little bit. So you'd have something like this for group 2, not necessarily drawn to scale here, I should point out, but they're going to have a trend that's similar to this, where when you go from group 1 to group 2, it increases, but then as you go back to group 3, it decreases a little bit because of the normally high ionization energy for group 2, and then similarly the trend kind of goes like that. It's going to have a sharp increase at group 5, come back down a little bit in group 6, and then you go from there. And what we should be familiar with also, and maybe it's better to draw it this way, is that the noble gas, the group 8 elements, those have the most stable configuration, completely filled S and P subshells, so those are going to be the highest ones and probably off the line a little bit too, but they're all the way to the right, so there's no real exception to worry about there. But you should be familiar with the idea that Group 2 and Group 5 are somewhat exceptions when it comes to this ionization energy trend, where they tend to be higher than you would expect, which gives you this discontinuity. It's not going to increase straight across. So that's something I just wanted to clarify from last time. Now what I want to finish up with ionization energies is talking about successive ionization energies. And so this is the idea that we can remove more than one electron from an element. So the ionization energy that we talked about and the one that you get from the periodic trends, as we just discussed, that refers to removing the first electron. Now if we remove additional electrons, we have additional ionization energies to consider, and each of them reflects removing one electron at a time. So IE1, the first ionization energy, is what we sort of described last time, which is just a neutral atom and removing one electron to make the cation with a free electron. Alright, so that's the first ionization energy. Now we can also define the second ionization energy, which is you're starting with the cations. You've already removed one electron. The second ionization energy is the energy required to remove a second electron. So we're going to start with the 1 plus cation and remove a second electron from that, making the 2 plus. And so on. So for however many electrons you have in your atom, you're going to have that many ionization energies associated with it. So the energy required to remove each additional electron. And what we should be aware of, we're comparing for the same element, if we're comparing the successive ionization energies, ionization energy 1, 2, 3, and so on, they're always going to increase, because as we remove electrons, we have less electron-electron repulsion, we have net positive charge, so they don't really want to lose any more electrons. So each time you remove an electron, it becomes more difficult to remove the next one, which means the ionization energies increase each time you remove an additional electron. Right? So it's harder to remove an electron from something that already has a positive charge, which we call a cation. Alright, so that's the true thing. And then if we look at the ionization energies for a successive element, we see that these are some real numbers. These are in megajoules per mole, kind of a weird unit, but a mole being a huge collection of these atoms, which we'll learn more about. So basically this is the amount of energy that's required to remove an electron from nitrogen, oxygen, when you're talking about a huge sample of those. So if we think about the configurations of nitrogen and oxygen, the valence configurations, which is what we're most interested in, is 2s2, 2p3 for nitrogen, and then we have 2s2, 2p4 for oxygen, so just one more additional electron in oxygen for its valence configuration. And so if we think about the ionization energies, well, for here, we notice that the first ionization energy for nitrogen is a little bit higher than oxygen. We said that that's one of those exceptions where it's abnormally high, so that checks out. But as we go across for each successive ionization energy, we see that they tend to increase. So a steady increase, a steady increase, a steady increase, a steady increase. And then all of a sudden at ion energy IE6, we have a huge jump for nitrogen. It goes from 9 to 53 after increasing only, a few megajoules each time. And then for oxygen, we see it's a relatively steady increase, a couple each time. And then all of a sudden, in the seventh ionization energy, we go up from 13 to 71. So a huge jump at some point. And so where that jump occurs is after all the valence electrons have been removed. So once you remove valence electrons, the core electrons are much more difficult to remove because they're in lower subshells that are closer to the nucleus compared to the valence electrons. So it's very difficult to remove core electrons. Remember, core electrons are the ones that are basically not the valence electrons, anything that's in the inner subshells. Okay? Okay, so nitrogen has 5 valence electrons, S2P3. And after we've gone through 5 ionization energies, which is removing all 5 of those electrons, removing the 6th electron, which is in the core, is extremely difficult, and that's why this number is so much larger. And then same thing for oxygen, 6 valence electrons, so removing the 7th is extremely difficult compared to removing the first 6. So anytime so when you compare ionization energies for elements, this is a way to sort of determine how many valence electrons they have, or you can at least predict then where the ionization energy is going to have that steep jump. Alright, so that's what I want to end with for ionization energy. There's one more periodic trend we're going to talk about that deals with just atoms on their own, or elements by themselves, which is electron affinity. So ionization energy, we want to keep these two straight. Ionization energy is the energy required to remove an electron, and then electron affinity is the energy change that's accompanied with adding an electron. So instead of forming a positively charged species, we're forming a negatively charged ion. Okay, so the electron affinity is the energy change accompanying addition of electron. Okay? And so the sort of general process we would write is you're starting again with a gas phase atom, just like we did for ionization, but this time instead of subtracting or removing an electron, you're adding one, and you're going to form another ion, but this time it's going to be negatively charged because it has an extra electron. Okay, so that's the process we're talking about when we refer to electron affinity. And so this change in energy, delta E as we call it, is equal to the first electron affinity. We're mostly going to deal with first electron affinities. We'll see some higher order ones a little bit later. But the first electron affinity is usually negative. So it's usually a negative number, and that's because we're adding an electron. That electron has a net attraction to the nucleus. Remember that whenever a positive and a negative charge interact with each other, you tend to have a negative change in energy or a negative energy of interaction. So electron affinities tend to be negative because adding one electron creates an additional attraction to the nucleus. And there's the factors that influence electron affinity are very similar, I guess almost identical to the factors that influence ionization energy. So if you talk about the size of the atom, there's sort of an inverse relationship. Larger atoms have smaller electron affinities. Now we have to be a little bit familiar with the terminology here. So when I say a smaller electron affinity, I mean a less negative. So they're almost always negative numbers. And so if it's a very large negative number like minus 500, we would say that's a large electron affinity. An electron affinity that's smaller in magnitude but still negative like minus 100, we would say is a smaller electron affinity. So large and small refers to the magnitude of that number, not to the sign. They're almost always going to be negative. So the larger atoms have smaller electron affinities, and that's because the electron that you're adding to those is farther away from the nucleus, so it doesn't have as strong of an attraction to the nucleus. And then just like we saw for ionization energy, this effective nuclear charge, which is the amount of positive charge that one of those outer electrons experiences, is also going to influence electron affinity. And in general, again, there's some blips in this trend, so we don't want to make definitive statements here. But in general, if you have a higher effective nuclear charge, that is, you're adding protons to the nucleus, that's going to lead to a larger, or again, more negative, as we say. When we say larger, we mean more negative electron affinity. Okay? So Z effective, as you add more protons to the nucleus, you tend to also increase the electron affinity, just like we saw for ionization energy. So that leads us then to the general periodic trend for electron affinity, which is going to look identical to the general trend for ionization energy. So we saw that ionization energy increases as you go up in the periodic table. That's because you're moving to smaller atoms as you go up. And then it's also going to increase as you go left to right, because as you go left to right, you're adding more protons to the nucleus, and you have, in that case, then more effective nuclear charge and a larger increase in electron affinity. So again, the trend that I'm drawing here, these arrows, reflects the direction you would move to increase or make the electron affinity more negative. Okay? Now we should be familiar with the trend for electron affinity is not as smooth as what we saw for atomic radius or even for ionization energy. So there are several exceptions to this trend that I'm showing you, and we don't want you to know all of them, but there's a few that you should be familiar with. And they also revolve around those two same groups of the periodic table where you have relatively stable electron configurations. So if you're going to group 2A, which is again the main group, the second column here in the periodic table, which has an S2 configuration, or if you're talking about group 5A, those two, again, they have stable configurations. Group 5A is this column here, which has a P3 configuration, half filled. Those tend to have, in this case, smaller electron affinity than you would expect. In many cases, they're even positive. So most electron affinities are negative. These ones are so small that they're actually, in many cases, positive numbers, meaning that those atoms don't want any extra electrons at all. And again, think about that from the standpoint of the electron configuration. These elements already have very stable electron configurations, so they don't want any more electrons. Because if they add an extra electron, they have to go to a less stable configuration. Okay, so we have this same break in the trend, group 2A and group 5A, that we talked about for ionization energy, but it goes in the opposite order. Ionization energy increases in these two groups because they don't want to lose any electrons. They also don't want to gain electrons, so that means their electron affinity then is a little bit smaller. So it's the same breaks in the trend, but in the opposite direction. And generally speaking, we can say that groups 1 and 2, so these are the main group metals, the S block of the periodic table over here on the left. Those tend to have the smallest electron affinities. So a general property of metals is they have small electron affinities. They don't want to gain any more electrons. And then finally, if we go to the other end of the periodic table, group 6A and 7A, so that's the oxygen group and the fluorine group. Those tend to have the largest electron affinity. All right, so they have those kind of basic trends that you want to be familiar with and a couple of exceptions. We should also remember we don't often include the noble gases in these discussions. This column here, the last column in the periodic table that has those very stable S2 P6 configurations, those have no measurable electron affinity. So those don't really fall onto this same basic trend either, because when you already have a full subshell, S and P subshell, they don't want any more electrons either. So we don't even really talk about electron affinities for the noble gases. Just be aware of the fact that they don't really have any affinity for extra electrons. They can't even measure those numbers because they're so small. Okay, so that takes us to the end of periodic trends. What we want to move into now is, so I think we've now finished chapter 2, I believe, if we're keeping score at home. And so now we're going into chapter 3, which is the last chapter that will be covered on the first exam, which is coming up in about 10 days, to freak you out a little bit. And then also, the homework assignment for this week will still be all chapter 2. So we everything that we cover today, for the rest of today, won't be on the homework, but it will be on the first exam. And so what we're going to start talking about in chapter 3 is, everything in chapter 2 is about individual atoms. What are the properties of those? What are the electron configurations of those atoms? And now we're going to move on to talking about what happens when two atoms come together and make a chemical bond. So the types of chemical bonds they can make, how do the electrons rearrange themselves, and things of that sort. So that's what's coming up in chapter 3 and even a little bit beyond that as we discuss this. So the first thing we're going to talk about are ionic bonds. And so this is what happens when we form ionic bonds is we have atoms that are completely losing or gaining electrons. They're going to either form a cation or an anion. And then because of those opposite charges, they're going to be really strongly attracted to each other. So they're going to pair up with oppositely charged species and make a very strong interaction. So in the case of ionic compounds, you're not really sharing electrons. One of the atoms is losing one or more electrons. One of the atoms is gaining one or more electrons, and then those net charges attract to each other. So the first thing we have to do is be able to predict for a given element what are the charges of the ions that are formed. And so for the main group elements, this is pretty simple to do. And the idea here is that they want to gain or lose electrons such that they approach the nearest noble gas configuration. They want to either gain enough electrons to have the noble gas S2P6 configuration, or they want to lose electrons to achieve that S2P6 noble gas configuration. So for each group of the main group elements, it's very predictable what ions are going to form. So if we go to group 1A, which is the sodium group, I guess lithium is the first one. These have an S1 configuration. And so if we go, I need to put a periodic table in these files because it's not fast to switch back and forth anymore, unfortunately. But if we go back to our periodic table here, group 1, we're excluding hydrogen because that's a nonmetal that doesn't behave the same way. But if we look at lithium, sodium, potassium, rubidium, cesium, all these group 1 elements, if they lose one electron, they're now going to have a noble gas configuration. So all of these have just one s electron, an S1 valence configuration, and by losing that single s electron, they would go back and have a configuration of whatever noble gas comes before them. Okay? And so these group 1A ions are all going to form then +1 charges because they just need to lose one electron to form a stable configuration. And so that means lithium, sodium, potassium, rubidium, and cesium all form +1 ions. And really that's the only type of ion they will ever form. There's never going to be an exception to that. If we go to the next group in the periodic table, S2, these are still metals. We're still on the left side of the periodic table. Group 2A has an S2 valence configuration, so not surprisingly, they want to lose both of those s electrons, and that will then give them the nearest noble gas configuration. So all the elements in this column, we're going to want to lose 2 electrons and form a +2 cation, and that's true of every element in this column. So you have beryllium, magnesium, calcium, strontium, and barium all form stable +2 cations that are going to be commonly occurring in ionic compounds. Okay? If we go then to group 5 of the periodic table, so if we go to group 5 of the periodic table here, in this case we have sort of the divider line. So some of these have more metallic character. Group 5 is over here. What am I doing? It's group 3. So as we go down, we do tend to run into some metals. But the first couple elements in group 5, the first 2 or 3, nitrogen, phosphorus, and arsenic, are nonmetals. And what nonmetals tend to do is they tend to gain electrons to be able to achieve the noble gas configuration. So if we have nitrogen here, nitrogen has a P3 configuration. If it gains 3 more electrons, it's going to have the same configuration as neon. So the nonmetals, the ones on the right side of the periodic table, tend to form anions. They gain electrons, however many it takes, to achieve the noble gas configuration. So group 5A tends to form -3 anions by gaining 3 electrons. Nitrogen and phosphorus both do this. There are some compounds that have formally arsenic as a 3- charge as well. So all of these are in that column of the periodic table where if they gain 3 electrons, they get to a noble gas configuration. Group 6A, so this is again the S2P3 configuration. Group 6A is S2P4. So if they gain 2 electrons now, they will have a filled P6 subshell. So they only need to gain 2 electrons, meaning they form -2 anions. So you have oxygen, sulfur, and selenium all do this. As you go further and further down these P blocks, especially for group 5 and group 6, the elements way at the bottom tend to have more metallic characters. They don't form anions. But for the ones that are up top, like oxygen, nitrogen, sulfur, phosphorus, all those, they behave like nonmetals and they gain electrons to form anions. And then S2P5, if we go to group 7A, so that's the halogens, they just need to gain 1 more electron to get to a P6 configuration, so these form -1 anions. And this is true for all members of this series, at least ones that are naturally occurring. So fluorine, chlorine, bromine, and iodine all would gain 1 electron to form -1 anions. Alright, so those are the ones from the main group. These are the ones that are easy to predict. We're not going to talk as much about transition metal ions. We'll talk a little bit about them when we start talking about the names of the compounds that include them. Transition metals, the ones that are in the D block of the periodic table, many of those can form multiple cations. So they do behave like metals. They tend to lose electrons to form cations, but it's not as easy to predict which ones they will form. So for example, iron forms +2 and +3 cations very commonly, but there's no way to tell from the periodic table that that's what you would predict. So we're not going to deal as much with transition metals. But for the main group, these are the ones you should be easily able to predict, and there's really no exceptions to these. The only other one we want to know that doesn't fall into these ones is aluminum. we should be familiar with aluminum forming a +3 cation. So aluminum by itself is S2P1, and it's able to lose all 3 of those valence electrons to form a stable cation. So we should be familiar with that one also, even though it's not in here with the rest of them. Okay, so aluminum does form a +3 cation. So those are the ions that are formed by all the main group elements. And now we can start talking about what is the electron configuration of these ions. And we kind of already dealt with this a little bit as we were discussing them. So for an anion, something that has extra electrons, all we do is we just follow the Aufbau principle and we add electrons to whatever the partially filled p subshell is. So we're going to add the additional electrons to the lowest energy available subshell, which is going to be the partially filled p group, p subshell. So as an example, if we have oxygen, the electron configuration from oxygen for the periodic table is 1s2, 2s2, 2p4. We should know now that the 2p subshell can hold up to 6 electrons. There's 3p orbitals, each can hold 2 electrons, so there's a maximum of 6. So when we form the oxygen 2- anion by adding 2 electrons, the configuration for that is going to be 1s2, 2s2, and then we put the additional 2 electrons still into the remaining spots in the 2p and make the 2p6 configuration, which is the same configuration as neon. So as I said, we want to achieve the nearest noble gas configuration, and so by adding 2 electrons to oxygen, we get to this stable neon configuration. So whenever you're forming anions and you want to know what the electron configuration of that anion is, you just add the additional electrons to whatever the lowest energy available subshell is. If we go to the cations for the S block, we're going to, in this case, remove electrons. And we always remove the valence electrons. So the valence electrons are the ones that participate in the chemistry. And so when we're talking about S block cations, we have to remove the outermost S electrons. Again, those are those valence electrons that have the highest value of N, the highest first principal quantum number. And so if we talk about sodium, 1s2, 2s2, 2p6, 3s1. So sodium has 5 total electrons that are in s orbitals. It has 2 in the 1s, 2 in the 2s, 1 in the 3s. The only one that's going to be involved in forming the ion is the outermost 3s electrons, the ones with the highest value of N. And so to form the sodium cation, we lose 1 electron. And that gets us to 1s2, 2s2, 2p6 configuration. So that s electron was lost altogether, and that's also the same configuration as neon. So in this case, by losing 1 electron, this outermost 3s electron, we also achieve a stable noble gas configuration. We never are going to touch these core electrons here in the 1s, in the 2s, and 2p levels. Those are going to be core electrons that aren't going to participate in any of the chemistry or forming ions or forming bonds of other types. All right, so that's sort of a little description of the electron configurations. And then the next thing we can talk about are the relative sizes of ions. So we dealt with periodic trends for atoms for atomic radius, and that, remember, says the atomic radius increases as you move down a column on the periodic table, and it also increases as you move right to left. So we know a periodic trend for neutral atoms, but that periodic trend only directly applies to neutral atoms. And so if we talk about cations and anions, what are the relative sizes of these? So the cations are always going to be smaller than the parent atom. And that's because we're removing the electrons that are furthest away from the nucleus. So the radius of an atom or an ion is basically, can be thought of in a simple fashion of, it's the distance from the nucleus to the outermost electrons. If we remove the electrons that are farther away, the cation is going to be smaller than the atom that it started as. And in general, if we increase the positive charge, we're going to have a smaller cation. So So the more positive charge we have, the more electrons we remove, the smaller and smaller that cation is going to get. And so as an example, this is not one we would be easily able to predict based on what we know, but lead, Pb, is a main group metal in the P block, and it forms two different cations that are found in many compounds. So it forms a 2+, and it also forms a 4+ cation. So two different cations formed by lead, and each time you remove more electrons, the cation gets smaller and smaller. So if we're comparing the radii of these species, the neutral lead atom is going to be larger than lead 2+, which is going to be larger than lead 4+. As you remove more electrons, they get smaller and smaller. All right, so that's the trend for cations, and then anions is the exact opposite. As you add electrons to anions, they're going to be larger than the parent atom. Now this one might not be as intuitive because we're still adding electrons to the outermost subshell. So we're not adding a new subshell to the atom, so why does it get bigger? But that's because as we add electrons, we increase the electron repulsion. So we're adding electrons to the outermost subshell. We're not creating a new subshell with electrons in it. But by doing so, we increase the electron-electron repulsion, which sort of pushes things a little bit farther apart from each other. So when we increase the electron-electron repulsion, those electrons in the outer shell want to get a little bit farther away from each other to relieve that, so they spread out a little bit. That last subshell becomes a little bit bigger. So it's not that we're adding a new subshell, we're just expanding the size of the existing subshell by adding extra electrons to it. Alright, and then finally the last comparison we want to talk about are what are called isoelectronic atoms or ions. I think we may have touched on this in another context a little bit earlier. But what isoelectronic means is that they have the same number of electrons. So these are species that have the same number of electrons, cations, neutral atoms, anions, some combination of those, that all have the exact same number of electrons. They would have different numbers of protons in the nucleus, which identifies them as different elements and gives rise to the different charges that they have. But if they all have the same number of electrons, the comparison of their sizes is very straightforward. So if we're comparing the radii of these species that have equal numbers of electrons, the ones that are more positively charged are going to be the smallest, based on the same arguments I've just told you. And then the ones that are neutral are going to be in the middle, so that whatever the neutral atom is that has that many electrons will be sort of intermediate in size. And then whatever anions we form that are negatively charged are going to have the largest radius in that series of isoelectronic species. All right? So as an example, we can start with argon as our neutral atom. So if we go to the periodic table and find argon, argon's over here, atomic number 18. So argon has 8 electrons. So let's think about some other species that also have, 18 electrons. Let's think about some other species that also have 18 electrons. It's atomic number 18. So if we had the potassium cation, K+, so K has 19, so we lose 1 electron to become argon configuration. Calcium 2+ would also have the same configuration, 18 electrons. Or if we look at anions, Cl-, S- would have all the same number of electrons. So all of those species would have 18 electrons, and if we compare their sizes then, we said we can form cations from the cations. They're going to all be smaller than argon. So K+ and calcium 2+. Calcium 2+ is the smallest because it has a higher positive charge, 2+. And then as we have negatively charged species that also have 18 electrons, Cl- has 18 electrons. It's going to be larger than argon. And then S2- has 18 electrons. It's going to be even larger because it has an additional negative charge. All of these species have the same electron configuration and the same number of electrons, but the size goes in that order because of things we talked about, electron-electron repulsion and attraction to the nucleus being the two driving factors for that. Okay, so as we go from left to right here, from the positive species to the negative, we have fewer and fewer protons in the nucleus, and so that's going to pull the electrons not as closely, not as tightly, so they're going to be expanded and a little bit larger. All right, so that's the sizes of isoelectronic atoms and ions. So when you're comparing the sizes of things in the periodic table, we'll have you do these on the homework quite a bit this week.
you should first check to see if they're isoelectronic. If they're isoelectronic, you just need to order them based on their charge. You don't need to think about it any more than that. If they don't have the same number of electrons, then you have to think a little bit more about which subshells are occupied, how many protons are there, all sorts of things like that. You'll see a lot of examples of that as well. All right, so let's talk about how we predict ionic formulas. So we've dealt with predicting the ions that can form from different elements and how we use the periodic table to help us determine that. We now know some properties of those ions, namely their radius. So let's talk about then how do they combine to form ionic compounds. So when we form an ionic compound, we're going to have positive and negative ions combining with each other, and you must balance the charge completely. So the charges must be completely balanced, which means however many positive charges you have to get completely canceled out by whatever negative charges. So you're going to have no net positive or negative charge when you write the formula for an ionic compound. This is one of the topics we expect you to know a little bit about for the PA test, so this could be a refresher if you had trouble with that. And so as an example, a very simple example, if we have sodium, we already saw that sodium forms a +1 cation. If it combines with Cl-, which we call chloride, that forms a 1- anion. Sodium is +1, chloride is -1. They're going to combine together in a 1-to-1 ratio to balance that charge and give the formula NaCl. Okay? So you just need one of each to balance the positive and negative charges. So that's a pretty simple one. And then we have, so when we write the formulas for ionic compounds, we have subscripts that tell us how many of each of them there are. And for that, we want to use the smallest ratio possible. So we saw for sodium and chlorine, we had one of each. So we could write the formula like this, with subscripts of 1 on each of them to tell us that we have one of each, but that's not conventionally how it's done. If there's only one of something, you just leave the subscript out and write it like that. So this is the conventional way to write it without subscripts. That means you have one of each. However, what would be wrong to do, and definitely not correct, is to write, for example, Na2Cl2 or Na3Cl3. Both of these formulas would have the charges balanced. In this case, it would be 2 +1s and 2 -1s, which cancel out. This would be 3 +1s and 3 -1s. But for ionic compounds, we always want to write the lowest whole number ratio. So that'd be 1-to-1 in these cases. So we wouldn't want to write those in that way. You always need to find the smallest ratio. So let's go through a couple examples of writing ionic compound formulas if we know the ions that they come from. So if we have calcium 2+ and O2-, sort of a shortcut way of doing this that I like to show if arithmetic's not your strong suit, is what we can do when we want to write the formula is we take the charge on one of the ions and we make it the subscript on the other. We take the charge on the second ion and make it the subscript on the first. We don't keep the plus and minus signs, obviously. Subscripts are always just positive numbers. And so by doing that, we get calcium 2O2, which we have to then reduce down to calcium oxide in the smallest whole number ratio, CaO, one of each. All right, so that's how we would get the formula for that. Again, that one's a fairly simple one because the cation and the anion just have opposite charges, so if you have one of each, you cancel out the charge. Now, one that's a little bit more difficult is calcium 2+ and N3-. They have two different charges, so we have to figure out how to balance those. And as I said, a shortcut way of doing this is just to take this charge and make it the subscript on the nitrogen, and take this charge 3 and make it a subscript on calcium, which gives us then Ca3N2. So this 3 becomes the subscript there, this 2 becomes the subscript on the other one. That's the smallest whole number ratio. You can't reduce that anymore. And if we verify that the charges balance out, for calcium we have 3 of them, that's what the subscript tells us, and it's going to be each of them 2+ charge, gives us +6 from the cations. And then nitrogen here we have 2 of them, each one has a -3 charge, and that gives us a -6. So the +6 from the cations balances with the -6 from the anions, and we're good to go. So this is the correct formula for Ca3N2 for calcium nitride, and there's no other way to write that in any simpler fashion. Okay, so we want to be able to do that. That's some stuff that should be a review for a lot of you from high school chemistry, but definitely brush up on that. Be able to predict the ions that are formed, and then be able to predict the ratios in which they combine. And we're not going to really talk in more detail about ionic bonding for now. There's some other details of that we're going to cover later on in the course, but when you have ionic compounds, you just have discrete positive and negative ions, and they're held together by electrostatic forces, the attraction between those positive and negative species. What we want to talk about in a little bit more detail are covalent bonds. So covalent bonds tend to involve nonmetals. So ionic bonds involve a metal with a nonmetal, one of each. One forms the cation, the metal forms the cation, the nonmetal forms the anion. But then for covalent bonds, we're typically talking about the overlap of two nonmetals. And the difference here is that instead of one atom gaining an electron and one atom losing an electron, or more than one, in covalent bonds we're sharing electrons. So this is a much more equitable arrangement of electrons. They're a little bit nicer to each other than ionic compounds are, and they share their electrons and don't actually steal them from each other. So that reminds me, one time, I should have mentioned this a little bit earlier when we were talking about positive ions and things. So a sodium atom went into a bar, and he was looking kind of upset. And the bartender said, "Hey, what's the matter?" And he said, "Well, I think I lost an electron." And the bartender said, "Well, are you sure?" He said, "I'm positive." All right, so we're going to move on now to talk about covalent bonds where electrons are shared. I don't have a joke about covalent bonds, so sorry. The comedy show ends now. Back to chemistry. But we're talking about shared electrons. So let's talk about sort of an energy diagram for what happens when two atoms approach each other and share electrons, and understand a little bit of why this happens in the first place, and some of the properties of these bonds that are formed. So what happens is I'm depicting the two atoms here. This x-axis here is internuclear distance. That's the distance between the two nuclei of the two atoms. So they're starting out over here on the right very far apart, and we're bringing them closer and closer together until at some point their electron clouds overlap with each other and the electrons are shared between the two atoms. We'll talk in more details about how that works exactly in the future, but suffice it to say we're bringing these atoms really close together such that their electron clouds start to overlap with each other and they share the valence electrons specifically. So when we start out here on the right side of our diagram, they're far apart from each other and they have no interaction. So they're basically just behaving as two free individual atoms. Okay, so there's no interaction between the atoms when they're that far apart. And so that means if we look at the potential energy, the energy of attraction between the two atoms, the energy that's sort of holding them together, there really is no interaction because they're so far apart. Now as we go further along and we start bringing the atoms closer together, eventually the electrons from one atom are going to start being attracted to the nucleus of the other. Okay, so as we've already talked about in the context of individual atoms, electrons like to form attractions with nuclei, and so once these two atoms get close enough to each other, the electrons from one atom are like, oh hey, there's some more protons over there, and they start side-eyeing them a little bit and trying to get closer to them. And so you start to see a little bit of a dip here in the energy as they start to attract each other. And then we get to some position where that energy reaches a minimum. And this is what we would call our covalent bond, where the electrons are completely shared, and you get to a minimum energy, meaning that those two atoms are attracted to each other as strong as they possibly can be. Now what happens as we start to bring them too close together is you get repulsions taking over again. Because if we try to force the electrons too close to each other into too small of a space, those electrons are going to start repelling each other, and if they get really close, the nuclei are going to start repelling each other. And so the energy goes back up to basically approaching infinity as you try to smush them closer and closer together. So there's sort of this sweet spot here where the two atoms are just the right distance to maximize the attraction between them. Okay? And we're going to talk in some detail about this on the next slide, but what I should point out is that the shape of this well, so we call this a potential energy well because it sort of has a well shape to it, a trough, if you will. And the shape of this is determined by the properties of the bond. And we'll talk about that in detail coming up here. Alright, so it's not that these numbers that I'm showing here have any real meaning. This is just an arbitrary scale that I drew. But each bond, each type of bond that we can talk about is going to have a different shape for this well, different profile, and different properties associated with it. All right, so let's talk a little about what those properties are then that we can sort of understand from this type of graph and some of the important properties to then be able to compare when we're looking at different bonds compared to each other. So one of those properties is called bond energy. This has a couple of synonyms that I'll give you. It's often referred to as bond strength, or a little bit more formally, bond dissociation energy. So those are two other things that we call it. And what it is referring to is the energy required to break the bond. Now, one thing I hate about this textbook is that they talk about bond energies in usually kilojoules per mole. We haven't really learned what a mole is yet, so you probably are all familiar with this, but we'll talk about it in a little bit. But it's the energy required to break a whole huge collection of bonds. So it's not just breaking one bond, it's breaking a lot of bonds at once. A mole specifically, which is a certain quantity that I don't want to get into the details of now. So when you see these units of kilojoules per mole, just be familiar with the fact that that mole refers to, we're talking about a huge collection of bonds, not just one individual one. And it's always in the gas phase, and we're talking about bond energy. Okay, so bond energy is defined as if we have two atoms bonded to each other. They could be two different atoms, they could be the same atom. I'll draw it as AB, which is in this case more like two different atoms. It's the amount of energy that's required to separate those into their individual species. So when we have bonds between two atoms, especially covalent bonds, we usually draw them as solid lines. That just went away. I accidentally erased it. We draw them as solid lines. So that means that the two atoms are bonded to each other. And then the bond energy is the amount of energy that it takes to completely separate those two from each other into individual neutral gas phase atoms. So the change in energy for this process is what we refer to as the bond energy, sometimes abbreviated as BE, for that bond. So a lot of times you'll see a subscript denoting what the bond is, in this case AB very generically. And that's going to be then larger than zero. It's always a positive number. It always takes energy to pull those atoms apart. And then finally the bond length, which is related to the atomic radius of the atoms. It's just the distance between the nuclei. So when two atoms are bonded to each other, we can measure how far apart the nuclei of those atoms are, and we call that the bond distance. So if we have our AB bond, let's say this is A, and then let's say B is even bigger. We have two atoms bonded to each other. They don't have to be the same size. Whatever this distance is between the two nuclei is what we call the bond distance. Okay? So it's that separation there. And one thing we should be familiar with, we'll talk about trends in bonds here more detail, but the bond distance is inversely related to bond energy. Okay? So that means if you have a longer bond, a bigger bond distance, you're going to tend to have a smaller bond energy, and vice versa. If you have a shorter or smaller bond, you're going to tend to have a larger bond energy. So that's kind of a correlation between those two parameters that we've just talked about, that they're kind of inversely related to each other. And if we have one of these potential wells here, like the one I just drew, we can use this graph to identify what those properties are for that bond. And so if we go to the bottom of this well here, if we go over to the y-axis, that's going to give us the bond energy. So this is the potential energy, and the bond energy is just the absolute value of that, or the negative of that. So if you find out how deep this well is, that tells you the bond energy. If you extrapolate to the y-axis, and then the x-axis value that sits at is what we call the bond distance. All right, so from these graphs, we can read off bond distance and bond energy. And there's a sample problem in a couple slides that talks about that. All right, some other properties of the covalent bond that we want to deal with. We have what's called bond order. So bond order is the number of bonding pairs that are shared between the two atoms. So each bond, we didn't really say this discreetly yet, but each covalent bond that we're forming is going to involve two electrons being shared. One electron from one atom, one electron from the other. Those two electrons are shared in the covalent bond. And the number of those electron pairs that are shared between the atoms tells you what's called the bond order. So we have three types of bond orders we're going to see in this class. We have bond orders of 1, 2, and 3. If we talk more about transition metal chemistry, which is, as I said, my favorite part of the periodic table, you can have bond orders of 4 or even 5 there. But for main group bonds that we're going to talk about, you have bond orders of either 1, 2, or 3. And so when you have a single bond, that's the situation when we say the bond order is 1. You have one shared electron pair, meaning two electrons are shared between the two atoms. So the way that we can draw this, and as an example of a single bond, a bond order of 1, if we form a bond between two hydrogen atoms, that's just a single bond, which means we just have one line between them telling us that it's one shared pair of electrons. Another way you'll see these drawn sometimes is we draw dots for each individual electron. And so a single bond would be drawn like that, two electrons that are shared between the two atoms. All right, that's a single bond. If we have a double bond, that means the bond order is 2. Two bonding pairs. So that means we have two shared pairs of electrons. So when we draw a double bond, we now draw two lines between them to indicate that there are two shared pairs of electrons. So when oxygen forms a bond with itself, it ends up being a double bond, and so you would draw that as a bond with two lines. Or alternatively, less common, but you could still draw it as now 4 shared electrons, 2 pairs that are shared between the two atoms, 4 dots being the 4 individual electrons that are involved in that covalent bond. And then we also have up to triple bonds, as I said, which would be a bond order of 3. Three bonding pairs. So nitrogen is a triple bond. So sorry, that's too many dots. So it'd have 3 pairs of dots that are shared, 3 pairs of electrons that are shared. And so that's an example of a triple bond or a bond order of 3. So we can have bond orders of 1, 2, and 3. We will learn sometime next week, I think, about how to predict what the bond order is for two atoms bonded to each other. Now, the importance of bond order for now is that it's another property of the bond that relates to the other two, the bond distance and the bond energy. So if you have a higher bond order, and this I think is fairly intuitive, if you have a higher bond order, you're sharing more electrons. That means there's a stronger attraction between those two atoms. So a higher bond order means you have a shorter bond because you're drawing things in a little bit closer to share all those electrons. You have a greater attractive force between those, and it correlates then with a stronger bond. All right, so for the higher bond order, that means the bond energy is higher and the bond distance is smaller. Okay, so that's another important relationship that we'll be able to use when we're predicting properties of bonds. All right, let's do one quick sample problem. So we have 2 potential energy diagrams shown here on top of each other. We want to give the bond energy and the bond length for the weaker of the 2 bonds shown. Okay, so remember that a weaker bond means you have a smaller bond energy. So we want to figure out which of these 2 bonds is weaker first. So remember, the strength of the bond or the bond energy we get by drawing over to to the y-axis. So this red one here has a bond energy of 300 kilojoules per mole as the scale. This blue one here, if I can draw my line straight, is 250. And so this one's going to be the weaker bond. It has a smaller bond energy of 250 kilojoules per mole. So that automatically eliminates this choice and this choice because those are the wrong bond energies. And then we want to figure out what is the bond length for that bond, and that's where we go to the x-axis. So if we go to this weaker bond here, we extrapolate to the x-axis, and we can clearly see that that's 150 picometers. So the bond length is 150. So the choice would be D for this one. So we want to be a little bit familiar with how to read these diagrams. I don't know for sure if this will come up on the homework, but it is something that's, I think, important for helping you understand how these properties work. And so that's just one example of the type of question we could ask you. All right, but we do need to move forward. And what we're going to move forward to now is one other periodic trend called electronegativity. Now, the difference between electronegativity and the other properties that we already learned, ionization energy and electron affinity, is that those two properties that we finished with at the beginning of today are properties of individual atoms. Electronegativity is a property of an atom when it's bonded to something else. So it's not a property of an individual atom, it's a property of an atom that's involved in a bond. So that's the key distinction here. And what's the definition? It's the relative ability of a bonded atom to attract shared electrons. So just because we form a covalent bond and we say that the electrons are shared, that doesn't mean that they're shared equally. Okay? So for example, if any of you had to share a room with your sibling when you were growing up, just because the room was shared doesn't mean that you guys share the space equally. Usually the larger and more aggressive sibling got more of the space. And it's sort of the same thing with covalent bonds. Not necessarily the larger in this case, but the atom that has the higher electronegativity is going to attract more of the electrons to itself. Now, I shared a room with my brother, but we were identical twins, so we got exactly 50% of the room each. But if you were with your little or younger, your older brother or younger brother or sister, you might have to unequally share that space. So electronegativity relates to that. And so the scale of the electronegativity is defined, the one that we use most often is defined by Linus Pauling, who's shown on this slide here. So the scale was derived by Pauling. He was a Nobel Prize winning chemist who spent a lot of his career at Caltech in Pasadena, California. And he came up with the electronegativity scale that's widely used today. Now it's a relative unitless scale, so it doesn't have like a real precise definition that we're going to get into, but we should be aware of some of the numbers that are involved. So the highest electronegativity on the periodic table belongs to fluorine. It's the most electronegative element, and its value we abbreviate this as EN, electronegativity, is 4.0. So it's a relatively compressed scale. It goes, the largest number on the whole scale is 4. And then the smallest one is going to be, if you go to the opposite corner of the periodic table, cesium or francium, really far down on the alkali metals, those have the smallest electronegativities, and the value that you get for those is 0.7. So like I said, it's a fairly compressed scale going from 0.7 to 4. But there are some trends associated with this that we're going to talk about. I wanted to give just a little bit of an insight into how these are measured. So the way that they got these numbers, and we're not going to worry about the details too much, but if you have a bond between two different elements, A and B, as we talked about, your expected bond energy, if the electrons were shared exactly equally, if there was no uneven sharing of the electrons, the expected bond energy would just be the average of the two individual bonds between the atoms themselves, AA and BB. Okay? So if the electrons are shared exactly equally, you would expect the bond energy to be that, the average of the two, for the two atoms that are involved. However, in reality, most bonds are different from this, and that difference is because of the unequal sharing of electrons, which leads to a little bit of an electrostatic attraction between them, which then causes that bond to be stronger than you would expect. So by measuring bond energies for all kinds of different bonds, Linus Pauling came up with a relative scale that ranks the atoms in terms of their ability to attract electrons. So he measured a bunch of different values, compared them all to each other, and kind of came up with a ranking system for electronegativity that's on this relatively small scale of 0.7 to 4.0. So that's where the numbers come from, but we just more need to know about what's the implications of these numbers and how do we predict electronegativity. So electronegativity, the periodic trend has the exact same format as the periodic trend for ionization energy and electron affinity. So it increases as we go bottom to top, and it also increases as we go left to right. So as I said, fluorine, we don't really talk about electronegativities for noble gases are not really defined because they don't really form bonds, so we only worry about everything up to group 7. So this one here, fluorine, as I said, is the largest, and the ones down here in the lower left corner are the smallest, and the trend kind of makes sense then from that. So as we go across the period, electronegativity goes up. As we go down a group, electronegativity goes down. That's opposite there. And we see that it's the same trend as electron affinity. And it's actually a very smooth trend. We don't really have any discontinuities in this if we're staying within the same row or same column of the periodic table. Sometimes it's hard to compare things that are diagonally related to each other because you might have two opposing trends that you're considering. But if you're comparing things in the same row of the periodic table, it's a very smooth trend from left to right, especially for the main group elements. And that's because electronegativity is very closely related to electron affinity. Electron affinity is the ability of an atom to attract an additional electron to itself. Electronegativity is the ability of an atom that's in a bond to attract an electron to itself in that bond. Now the reason you don't have these discontinuities for electron affinity is because once something forms a bond, as we'll learn later on, it has a full set of 8 electrons, including the ones that are shared. So electron configuration doesn't really matter anymore for electronegativity. All that really matters is the size of the atom and the nuclear charge. And so that's why the trend is much smoother for electronegativity. We don't have to worry about any exceptions here. Okay? So no exceptions to worry about here. I guess I should write that so that if we come back to this, you don't have to try to scratch your head and think, are there any exceptions to this? No, there's no exceptions as long as we're not considering noble gases which don't have electronegativities. All right, and the importance of electronegativity then is it allows us to predict a property of a bond that's called bond polarity. All right, so bond polarity occurs whenever we have atoms with two different electronegativities bonded to each other, and this is that situation I talked about where they don't share the electrons equally. So when you have atoms with different electronegativities and they're bonded to each other, you're going to have an unequal sharing of electrons. And that's going to lead to what's called polarity, which is an imbalance of the charge. So whatever bonding pairs we have are going to be shared unequally. And the result of that is that you have an imbalance in charge. You're going to have one side of your bond is going to have a little bit more negative charge. The other atom in the bond is going to have a little bit of positive charge. In total, they cancel out, and it's not a full positive and full negative charge. It's a partial positive, partial negative charge. But that's what we refer to as polarity. So if we have hydrogen and fluorine bonded to each other, very simple molecule, but now with two different elements involved, the electronegativity for hydrogen is 2.1. We don't want to memorize these values, obviously. But as I told you, fluorine is the most electronegative, 4.0. So there's an imbalance of charge, and so we indicate that in a couple different ways. We show either an arrow here, which is like a vector pointing towards the more negatively charged species, telling us that there's more negative charge over here. So this is one depiction, but I don't think it's the most common one that we'll see. So the arrow points towards the more electronegative atom, indicating that there's an imbalance of negative charge on that part of the bond, on that atom. But the more common way to draw it, which is a little bit more clear in this case, is if we have this bond, you draw lowercase Greek letter delta with a positive, lowercase Greek letter delta with a minus. So little delta means partial in this case. It means you have a partial positive charge on hydrogen, a partial negative charge on fluorine. You don't have a full +1 and -1 charge, but there is an imbalance there, and the electrons are not evenly distributed. So this is a more common way of indicating bond polarity. and you have a partial negative charge on whatever the more electronegative atom is. So when you have two atoms bonded to each other, if you know which one's more electronegative, you know which one's going to have more of the negative charge. Okay? So that's the situation with bond polarity, which comes from any difference in electronegativity. Now, the importance of this difference in electronegativity is that it allows us to predict how polar a bond is. So if we have a bond AB, this delta En, difference in electronegativity, is whatever that difference is between the electronegativity of one atom and the other. Alright? So when you have two atoms bonding to each other, if you take the electronegativity values and you subtract them to find the difference between them, that's your delta electronegativity. And if you have a perfectly covalent bond where the electrons are shared exactly equally, that means there's no electronegativity difference. So in order to have a truly covalent bond, you need to have two atoms that have exactly the same electronegativity. This is rigorously only true when you have two of the same atom bonded to itself. And so whenever you have the situation where you have the same atom bonded to itself, and the electronegativities are then the same, of course, we call that a nonpolar bond. Nonpolar or perfectly covalent, two different ways of saying the same thing. And so whenever you have diatomic elements like H2, Cl2, O2, etc., those are two of the same atom bonded to each other. They have the same electronegativity, so that means they're going to share the electrons perfectly equally. Now you should be aware that there are some elements where it's two different elements that coincidentally have very close to the same electronegativity. So carbon and sulfur, I think, is an example where the two electronegativity values are almost identical. So that bond would be not very polar at all because they have the same electronegativity. The electrons would be shared very equally. But rigorously speaking, that's not truly a nonpolar bond because to some level there's going to be at least a very, very slight electronegativity difference between those two, even if it's not reflected in the relatively imprecise scale that we use. So it's really only true if it's two of the same atoms, but there are a lot of other bonds where the two atoms have very close electronegativity values that would also be considered largely nonpolar. But then if we have polar and ionic bonds, we have differences in electronegativity. And so if our difference in electronegativity is somewhere between 0 and 2, so it's greater than 0, meaning the two atoms have different electronegativities, but they're not so different from each other such that the difference between them is 2 or less. These are approximate cutoffs. They're not really rigorous cutoffs. We call these in general polar covalent bonds. So in this case, we would still classify the bond as covalent, but we would say it's a polar bond because the electrons are shared unequally. And then alternatively, if we have our difference in electronegativity is greater than 2, these are the types of bonds that we conventionally refer to as ionic bonds. All right? Now what I want to emphasize here is that there's no real cutoff between polar, covalent, and ionic bonds. In reality, there's a continuum that starts at nonpolar covalent bonds and progresses until you get to what we classify as ionic bonds. Okay, so there's no fundamental difference between ionic and covalent bonds. It's just the difference in electronegativity is bigger for the bonds that we consider as ionic. And so another way of saying this is that the higher the difference in electronegativity, the larger that difference, we say that's a larger percent ionic character. So ionic character is how close is that bond to being a truly ionic bond where one atom steals an electron completely from the other, and the difference in electronegativity tells you how ionic that bond is. So there's these are some things to keep in mind about bonds, that there's not really two different types of bonds. It's all just one type of bond that has different properties depending on how different the electronegativities are. Conventionally speaking, though, if it's two nonmetals bonded together, we call that a covalent bond. And if it's a metal with a nonmetal, two things from opposite ends of the periodic table, those are what we typically classify as ionic bonds. So even though there's not a fundamental difference between them, at least in the chemistry lexicon, we still tend to classify them as distinct things. And then there's this simulator here that I gave you the link to that I think is a good one to help us understand bond polarity. So I encourage you to check that out on your own time. All right, the last thing I want to talk about with covalent bonds is the idea of using bond energy to calculate delta E for a reaction. Now, this is one of those topics in the book that feels a little bit out of place to me. The book authors made some interesting decisions in terms of how they ordered things, and this is one of those things. But essentially what we're doing here is we're taking two sets of elements or compounds, two or more elements or compounds, and we're reacting with each other to form something different, and we want to know what is the change in energy for that process. These are details we're going to see a lot more of much later on in the course, but if we have a delta E for a reaction, it's the change in internal energy when reactions convert to products. So whenever we have some sort of a chemical reaction taking place where we're breaking bonds, forming new bonds, we're going to have a change in energy because the bond energies that we have on the reactant side are in most cases not going to be the same as the bond energies we have on the product side. Another way to think about this is that this is the amount of heat that's either absorbed or released by the reaction when the bonds form, when the new bonds form. And so the way we're going to do this is if we know the bond energies for all of the bonds that are involved in the reaction, we can break all the bonds on the reactant side. So this requires energy input. Which means the change in energy for breaking all the bonds is a positive number. As we said, breaking a bond always requires us to put energy in. So we have to do that to break the bonds on the reactant side. Which when we're writing a chemical equation, that's the left side of the equation. And then on the other side, we're going to form the new products that are part of this chemical reaction. And so we're going to form a bunch of new bonds, and that's going to release energy. So when we form bonds, we have a different quantity of energy is going to be released by forming the bonds. Or I guess almost always a different quantity, unless there's some happy coincidence involved. We're going to release a different quantity of energy by forming the bonds. Which means the delta E for forming the product bonds is going to be a negative number, less than 0, when the atoms that we have from our reactants rearrange to form the new products. Okay? And so that gives us a pretty simple equation then for calculating the delta E for a reaction if we know the bond energies of all the bonds on the reactant side and we know the bond energies of all the bonds on the product side. So it's going to be the sum, so there's another Greek letter, capital sigma here. It's the sum of all the bond energies on the reactant side minus the sum of all the bond energies on the product side. Okay, so bond energies are positive quantities. We put this much energy in to break all the bonds on the reactant side, and we release this much energy when we form all the bonds on the product side, and then we add those two together to get the difference between the reactants and the products, or the overall delta E for the reaction. Okay, so this Greek letter sigma means sum. That means we add all of them up. And again, this abbreviation BE means bond energy, or as I said, sometimes referred to as bond association energy, bond strength. It's that given quantity for however strong the bond is, however much energy is required to break that individual bond. So let's close up then with an example problem on how to do this. These are a little bit tedious at times. They take a bit of work to do. But let's say we're doing this reaction here. So we have a reactant that has carbon with a single bond to two hydrogens and a double bond to oxygen. It's reacting with pH3, which is going to be phosphorus with three single bonds to hydrogen. And then that's going to form this product here that has all single bonds. All right, so let's, and then we're given all this information. We have the bond energy values for a CH bond, a C double bondo, a C single bondo, pH, all these different bond energies that we're going to use to calculate the delta E for this reaction. So on the reactant side, let's figure out what bonds we're breaking. And so the best way to do this is just to break all the bonds. Even though some of the bonds stay intact on the product side, I think it's easiest to just break every single bond on the reactant side and form every single bond on the product side. There will be some redundancy there, but it's a lot easier than just trying to keep track of which bonds are all broken and formed. Anyway, so what we do is we look at the reaction side. This species here has two CH bonds, one there and one there. And so we're going to take this number, the bond strength for CH, and we're going to multiply it by 2. We have to count for how many of those bonds are. So it's going to take 826 kilojoules to break those two CH bonds. We also have one carbon-oxygen double bond, 2 lines there. So this is the number used for carbon-oxygen double bonds, 745. So there's one of those. So that's another 745 kilojoules. And then finally, we have this pH3, which is going to have 3 pH bonds. All right, and that's the only bond energy we're given that involves phosphorus and hydrogen, so that's one we use. So we have 3 of those. Each of those has a bond energy of 320. All right, so that's the bond energy for the reactants. And then if we go to the product side, which I'll do on the next page because we're going to run the space here. On the product side, if we look at, we only have one product. This also has 2 CH bonds, one there, one there. So same number we used before, 2 times 413. Our product side now has a carbon-oxygen single bond. So this has changed from a double bond to a single bond. So we're going to use that number there, 358, for carbon-oxygen single bond. We have an OH bond that's formed there. So OH we're given is 467. We have one carbon-phosphorus bond. So we have this bond here in the product, carbon-phosphorus. The number for carbon-phosphorus is there, 264. So if you're not given all of these bond energies, you can't really do this type of problem. So all this information should be given to you. You just have to make sure you use the right numbers for each of those. So that's 264 for carbon-phosphorus. These are all given quantities. And then finally, for the last thing we have are 2 phosphorus-hydrogen bonds left in the product. So there's the structure of the product, 2 phosphorus-hydrogen bonds. Each of those, we already used that number, is 320, but now there's only 2 of them in the product. So 2 times 320 is 640 kilojoules. And then we just have to add both of these up individually. So on the reactant side, the sum of the bond energies for reactants is just going to be these 3 numbers all added together. And so I got 2,531 for the sum of the bond energies on the reactants. We need to add up all the bond energies on the product side. Which is a little more complicated. Now we have these 5 numbers to consider there. We add all 5 of those together, and we get 2,555. And so finally we have the two numbers, one for reactants, one for products. Delta E is just going to be the subtraction of those two. Sum of the bond energies for the reactants minus the sum of the bond energies for the products. So we had 2,531 kilojoules for the reactant bonds. We formed 2,555 kilojoules worth of bonds on the product side, so we subtract those two numbers and we get a minus 24 kilojoules. As it turns out, a relatively small delta E, but we still see there's a difference between reactants and products. So that's a typical type of problem. You'll want to practice that as well. And we'll see you next time with some more things about molecular structure.